So in this video, I want to do another Galois theory computation. I want to look at another polynomial, this time f of x equals x cubed minus 2. This is basically section C in the problems in this chapter. Since this is our last week, I don't see the need to give us extra homework and follow our rigid, theorems, examples, homework format. I just kind of want to illustrate what's happening. And Pinter gives a relatively slick sketch of a solution in this section. And he sort of relies on, I don't know how I should explain this. He relies on the fact that this is a low degree irreducible polynomial to get the conclusion that he wants. I want to sort of roll up my sleeves and work a little harder. With the primary reason being, or maybe I should say primary reasons being twofold, is first, I think it's worthwhile to sort of get your hands dirty and see how these things really work. And second, I'm hoping that at the end of this, I can tell us the main theorem of Galois theory, and then we'll be able to see sort of how the calculations we've done relate to what that theorem is saying. And so the main theorem for this video, I think I'm going to just let you guys read that in Pinter because it's kind of just a sequence of little lemmas. I don't think it's very hard, but I think we'll get the idea best by continuing to work examples. So for this example, we want to determine the Galois group of this thing. And so we've seen before that when you have a polynomial of this form, then the splitting field becomes Q adjoin the real cube root together with a root of unity. Well, what do the root of unities look like? We know that we have Euler's formula. Right? So I can write down what this expression looks like. I have to figure out how it relates to Q. And so for that, I always have to draw the picture because I cannot memorize trig formulas to save my life. So 2 pi over 3 is like this one, and 4 pi over 3 is like this one, and then here's the real one. 2 pi over 3 is it's the closest, right? This is a pi over 6 angular defect. So this is minus a half, and that makes this plus square root of 3 over 2 I because of Pythagoras. And so what stuff in this omega 3 is already in Q? Well, certainly the 1/2s are. It's only the square root of 3I that are not. So we can write this as Q adjoin the cube root of 2 and also the square root of 3I. Okay, so the next step is I need to know the degree of this extension. In other words, I have to calculate Q adjoin cube root of 2 square root of 3I over Q. And let's see, the simplest way to do that is, well, we know this is clearly irreducible over Q because if a polynomial such as this is reducible over Q, it has a linear factor. And you could use the rational root test, for example. So it's definitely an irreducible polynomial. On the other hand, we can work out using the Tower law. Like I could separate, let's go back to this version, right? Since these fields are the same, let's use the original version. Q adjoin cube root of 2 and also omega 3. Let's think about that as just over Q cube root of 2. Is that the way I want to go? Yes, because we know that omega 3 has minimal polynomial. Right? We saw in our example on the cyclotomic and roots of unity equal to x squared plus x plus 1, which is degree 2. And notice that while this is defined over Q, we're not using that cube root of 2 anywhere. It doesn't help us. And so that means this must be 2. On the other hand, I know what Q adjoin cube root of 2 has degree as. Sorry, that's not how you write that. Over Q itself, that's 3. And so putting these together, the whole field, which probably I should stop writing and just like name it K or something. I think I'm going to do that going forward. By the tower rule, that is 3 times 2 or 6. So now I know the order of the Galois group, right? This is equal to the order of the Galois group of K. Pinter uses colon notation over Q. Okay, so now in order to investigate further, we know that Galois groups, sorry, not Galois groups, we know that groups of order 6 can be classified by essentially one property. They're isomorphic to S3 if they are non-abelian, and they're isomorphic to Z mod 6Z when they are abelian. And so the question really is this group abelian or not? And so the way that we're going to do that is basically by specifically investigating the group, figuring out, what automorphisms we can find, and then just seeing if we can rig them up so that they commute or don't. And since 6 is a pretty small number, there just really aren't that many things that can happen. So I can find, kind of at a glance, 2 automorphisms that seem like ripe candidates. Because let's remember, we also know something about S3 and S3 and Z mod 6Z. This thing decomposes into Z3 cross Z2. And this thing doesn't have any such nice decomposition. But the point is, they both have to have elements of order 3 and 2. Because of Cauchy. Right? That's Cauchy's theorem. And so, if I find an element of order 3 and an element of order 2, those elements in particular will have to either commute or not. And they will be the witness of whether or not these things commute, because we know if I look at like 1, 2, 3 and 1, 2 in S3, that's not the same thing as 1, 2 and 1, 2, 3. And so, in other words, my strategy for determining the isomorphism type is to spot 2 relatively simple to spot automorphisms, and then use those, like calculate what is the composition of those automorphisms in each order. Did they commute or not? And that will diagnose for us which is which. Okay, so towards the automorphism of order 3, we know that what we should do is look at something involving the cube root of 2. So let's call this automorphism sigma. It should send 1 to 1. It should fix the square root of 3i, because we're not interested in that right now. And then the natural thing to do, if I want to like multiply cube root of 2 times something in a way for which if I do it 3 times, it has to return to itself, is to just multiply by that third root of unity. It remains to see that this is an automorphism, but let's hold that thought for just 1 second. Let's also talk about the order 2 automorphism, which is also not very hard to see. It should send 1 to 1, and it should leave the cube root of 2 alone. Let me write this down, kind of side by side, so the pattern kind of follows. And then let's send the square root of 3i to minus the square root of 3i. The first thing I want to call your attention to is that this is basically just complex conjugation, right? Because this is a, quote, real number. I mean, it's a rational number. It's an, okay. Yeah, I didn't have to say air quotes, actually. I could think of this as living inside the complex plane. And if I did, then this would be a normal real number, not some purely algebraic abstract nonsense. Since this is a real thing and this is a real thing, only this thing has any kind of imaginary stuff, and I am reflecting over the real axis in the complex plane. So this thing is kind of like complex conjugation. And this thing is, well, I don't want to say it's a rotation because I'm not moving this at all, but it's somehow, it's like a rotation. I'm not going to write that on the board because it's nebulous what I may mean by that. But this is literally complex conjugation on the nose. I suppose, on the other hand, if you have the intuition that it's like a rotation, then you might use your geometrical intuition to figure out which one of these it should be, but we'll still have to prove it. So the next thing to do is to convince ourselves that these things are automorphisms. So we have a question. Why are these field automorphisms? For this one, I think it's kind of clear that this guy's okay, right? I'm not really sure what there would be to say about it. In some sense, it seems obvious to me that this function plus respecting addition and is, well, it's fine, right? The only possible issue with any of these is, do they respect multiplication, and can they be a bijection? And I feel like both those things are very straightforward because I'm not really doing all that much to this, right? Here it looks a little bit more complicated. The reason that this works is because we know something about field automorphisms. In particular, each of these is being sent to another root of the minimal polynomial. And we already saw such things give field automorphisms. Right? Like this thing being a little bit complicated feels slightly suspicious. But if I multiply, right, if I were to plug in the cube root of 2 into here, or the cube root of 2 times the third root of unity, it would still be a root. And so since I'm sending a root to a different root, there must be a field automorphism that does what I want. Okay. So now, since we know these elements explicitly, these automorphisms explicitly, let's try to calculate them and see, is sigma tau equal to tau sigma as functions on this splitting field K. The easiest way to see that two things are different as functions is to plug in a specific value and see what happens when I look at them. Like, did I get the same thing on a specific number? So since the cube root of 2 here is the one that looks to be the most suspicious, let's try plugging in the cube root of 2. So let's calculate what is sigma tau of the cube root of 2. Well, tau of the cube root of 2 is just the cube root of 2 again. And sigma of the cube root of 2 is the cube root of 2 times omega. On the other hand, tau sigma of the cube root of 2 is tau applied to the cube root of 2 times omega. Since tau is a field automorphism, it distributes over these things. And we know that tau acts by complex conjugation. And so in order to understand what happens with omega 3, we can either use the fact that we know this is complex conjugation. Sorry, I think I'm getting a tiny bit ahead of myself. I can either write out omega 3 equals minus 1/2 plus the square root of 3 over 2i. And then C, because this is a field automorphism, tau of this must respect the addition. It fixes the normal real part. And in fact, it also respects multiplication, so the 1/2 can come out. And then we know on this thing it acts by flipping the sign. And so this is complex conjugation, which is what I said it would be. On the other hand, if you know that this is complex conjugation directly, then you could just infer that. And the magic about roots of unity is that if you have an omega n complex conjugate to some power, this gets you the same thing, but to the minus power. just because all the roots of unity have length 1 on the unit circle. This is also the same thing because omega to the n, omega n to the n power is equal to 1 as this guy. And so therefore, omega 3 complex conjugate is the same thing as omega squared. So all of this was a lot of fancy words to say that what we get out of this is a cube root of 2, not times omega 3, but times omega 3 squared, or omega 3 complex conjugate, however you think about it. So regardless then, what we've seen here is that these things are not the same. So the calculation went off basically without a hitch. The answer is no. And so therefore, this Galois group must be isomorphic to S3. Okay, this video is getting long enough. I want to continue. I'm going to chop this in half here. That way, I think this is a natural stopping point, but we're going to resume like right here in like 5 seconds, or at least I'm going to resume here in 5 seconds, because now I want to talk about the main theorem of Galois theory, but I also want to give you guys time to get up and go get some water or whatever, take a moment and process what we said. See you in a sec.